Hi, my name is Wendy and I'm gonna talk about green one-spot synthesis of biodiesel from Ricinus communis seeds by direct heterogeneous catalysis. Energy demand and the finite nature of fossil fuels reserve have motivated the search for more sustainable energy sources. A promising approach to mitigate energy and environmental problems is the use of clean biofuels. In this sense, biodiesel can provide a significant contribution since it is a sustainable, renewable, non-toxic, biodegradable, and offers a reduction in dioxide carbon emissions. Biodiesel is a mixture of fatty acid alkyl esters derived from renewable feedstocks such as vegetable oils or animal fats. And the most common reaction is the transesterification reaction that it's used in catalysis. And the most common use is the homogeneous catalysis that it's like hydroxide of sodium. In this case, we were using heterogeneous catalysis because it's more sustainable and it's not toxic, and we can reuse it more times than an homogeneous catalysis. In our experimental section is divided in three stages. The first one is the synthesis of catalysis, the second one the preparation of the seeds, and the last one is the production of biodiesel. In the first one, the catalysis was made by solid state in the conditions of 900 degrees and 6 hours, and we were using the zirconate of sodium as catalysis. Well, in our second section, in the preparation of the seeds, first of all, we have to remove all the shell that is in our seed. Afterwards, the Ricinus communis seeds were broken separately using an agate mortar to achieve the optimum oil extraction from the core of the seeds. Finally, in the third step, there is the production of biodiesel. We did it in two different ways. The first one, it was the conventional, that is using an homogeneous catalysis, and the most common is hydroxide of sodium. And then we were using the heterogeneous catalysis, that is the other way, that is using the zirconate of sodium. And we did that because we want to compare the one that is most using, that is the homogeneous, and compare this one that we were studying. And while the Ricinus communis seeds were mixed with NX10, dichloromethan or methanol, then the catalysis and a mixture with the molar ratio 1:15 oil methanol were added. The reaction time was evaluated by a kinetic reaction between 0.50 and the 24 hours. Based on the solvent added in the reaction, the direct transesterification was conducted by conventional reflux. The reaction mixture was separated by filtration without more solvent or water, and the oil phase was evaporated. An analysis of vegetable oil using electrospray ionization mass spectroscopy was performed, and the oil was found to contain several lipids such as triglycerides, D-monoglycerides, and free fatty acids, in specific the eicosanoic and rinoleic acid. Then the amount of catalysis was varied between 1 and 10% of weight, catalysis oil-weight ratio, and the second figure shows the flame produced with 1, 3, 5, 6, and 10 weight% of the zirconate of sodium catalysis for 6 hours at 65 degrees. The conversion increased as the amount of catalysis increased from 1 to 5 weight%, varying from 22 to 98.50% respectively. The optimum catalysis amount was at 5% of weight, and the flame yield was 99.99%. The figure number 3 shows the kinetic curves of flame yield versus the direct transesterification reaction time of the Ricinus communis seeds. This shows the comparison between the homogeneous and heterogeneous catalysis yield. And we can see that heterogeneous catalysis is around 82 to 80%. That it's in the period of 1 to 2 hours. And in the hours of 7 and 8, it's almost like a 93%. That it's the same as we were using the homogeneous catalysis of hydroxide of sodium. In the figure number 4, we can see the spectra of the flame production with the direct transesterification of Ricinus communis seeds catalyzed by zirconate of sodium. And we can see that we have the 3-methyl ester, that it's the formation when we are producing biodiesel. So with this spectra, we confirm that we produced biodiesel using the zirconate of sodium. In the figure number 5 and C, we can see the compositions and yields of FAME. For example, we can see fatty acid methyl esters like linoleic, oleic, or stearic. And well, in conclusion, the maximum yield of the FAMEs was 99% with respect to the oil extract, 52% from the Ricinus communis oils, and 4 hours of reaction time and 5% weight of catalysis. Then, the heterogeneous direct transesterification resulted in 7 times greener process compared to the conventional process, and a 3.5 times greener process than the homogeneous one-step process. Actually, this heterogeneous one-step process is almost 10 times less hazardous than the conventional process and 5 times less harmful than the homogeneous one-step process. So, heterogeneous direct transesterification is a promising alternative for more sustainable, cleaner, and efficient FAME production that is crucial to developing new technologies. And that's it. Thank you all for your attention. If you have any doubt, you can ask me in my email.